video, we will explain the type of analytic geometry that relates to our model, which is the sand clock, also known as an hourglass.
We will also explain why this shape is suitable for representation using analytic geometry, especially the hyperbola.
The material that we use are plastic bottle, wooden stick, sand, shoes box, and used Play-Doh.
The sand clock model is mainly related to the hyperbola, which is one of the conic sections that we have learned in the analytic geometry. Conic sections are the curves that form when a plane cuts through a cone, and they include hyperbola, parabola, and ellipse.
In our case, the shape of the sand clock looks like two cones placed tip to tip. When you take a vertical cross-section to the center of the hourglass, the outline that you will see is very similar to the graph of a hyperbola.
A hyperbola is made up of two separate curves that open in opposite directions. They are symmetrical about both the x-axis and y-axis. That's exactly how the sand clock looks. It has narrow waist in the middle. The top and bottom parts open outward in opposite direction, one upward and one downward. If we split the sand clock vertically and horizontally through the center, both halves are mirror image. There are several reasons why the hyperbola fits the sand clock model perfectly. First, it is symmetric. The hyperbola is symmetric about both axes, just like a sand clock, which looks the same on top and bottom. Second, it is narrow-centered. The hyperbola naturally has a narrow center near the origin, representing the point where the two glass bulbs of the hourglass meet. Third, it is smooth curvature. The smooth, gradually widening shape of a hyperbola matches the smooth glass contour of a real sand clock, allowing sand to slide down easily. So the first question asks us to write the equation of the hyperbola. First, we need to sketch the hyperbola graph with the vertices given, which are 5, 0 and negative 5, 0. And the foci are set 34, 0 and negative set 34, 0. As we already know, the formula for equation for hyperbola is x squared over a square minus y squared over b squared equal to 1. So, a is the distance from the origin to vertices. In this case, the origin is 0, 0. So, the value of a is 5. Next, c is the distance from origin to the foci. So, c is 34. Then, b is distance from origin to this. In order to find value of b, we need to use the theorem Pythagoras formula. Rearrange the formula and insert the value of a and c into the formula. And you will get b squared equal to 9. Next, insert all the value in the equation of hyperbola. The final answer will be x squared over 25 minus y squared over 9 equal to 1.
Okay, next, the question asks to find the equation of asymptotes. Okay, firstly, as we already know, the formula for equation of asymptotes is y equals 2 plus minus bx over a. So, we already found the value of b squared in the first question. Next, we just need to find the value of b, which will be b equals to 3. Then, we just need to insert all the value into the formula, and the final answer will be y equals to plus minus 3 over 5x.
Okay, for the last question, the question asks us to determine whether the point 73 lies inside, outside, or on the hyperbola. Okay, to solve this question, we need to use the equation of the hyperbola that we already got in the first question. So next, we just need to substitute the coordinate 73 into the equation, and the answer will be 0.96. So 0.96 is less than 1. So the final answer will be coordinate 73 lies inside the hyperbola.
To conclude, the sand clock model is based on the hyperbola in analytic geometry because of its symmetrical shape, narrow center, and smooth opposite opening curve.
It is a perfect example of how we can use analytic geometry to analyze, design, and understand real-world forms using mathematical equations. So, that's all from us. Bye!